Hello students, welcome to EPG Pathshala. I am Dr. Sanjay Kumar Chamoli from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Nuclear Models Part 9 from paper Nuclear and Particle Physics. After studying this module, you will be able to understand number 1, the basics of nuclear collective model. Number 2, knowledge of collective vibrational model. Number 3, knowledge of collective rotational model. Collective model. In this particular slide, we are going to study a new model which is called the collective model of nucleus. Collective model combines both liquid drop model and the shell model. Beauty of the collective model is its ability to explain. Beauty of the collective model is its ability to explain the low-lying excited states in heavy nuclei. So now we have understood that this collective model is nothing but a combination of the earlier two successful models like liquid drop model and shell model. This collective model can explain the low-lying excited states in heavy nuclei. So it means for heavy nuclei, this collective model can be applied and it is very successful in explaining their properties. A net nuclear potential due to filled shells exists and valence nucleons move independently under the influence of core potential. So this is basically the observation we have, that a net nuclear potential due to filled shells exist and valence nucleons move independently under the influence of this core potential. Interaction between outer, which are basically valence, and core nucleons lead to permanent deformation of the potential. So this is basically a very important thing, that how the deformation comes into picture or how the deformation arises in nuclei, that the interaction between valence nucleons and the core nucleons lead to permanent deformation of the potential. Collective model. Deformation represents collective motion of nucleons in the core and are related to the liquid drop model. So in the discussion about the nuclear models, we basically now in this slide will discuss the collective motion, that how it is produced. Now the deformation of the nucleus is an essential component. So deformation represents collective motion of nucleons in the core and are related to liquid drop model. So in the collective model is basically what we have understood up to the previous slide, that it is the coherent motion of the valence nucleons within the core. All type of collective motions, two type of collective motions are observed in nuclei. The two types are vibrations and rotation. That is, when the nucleons move coherently, they can produce an effect like vibration of an object or rotation of an object. Vibrations are nothing but surface oscillations, and the vibrations can be observed in both spherical nucleus as well as deformed nucleus. On the other hand, rotation type of collective motion can be observed only in deformed nuclei. Why it is so? Because quantum mechanically the spherical nucleus doesn't have any preferred direction, so rotation cannot be observed. So deformation is an essential component in observing rotations in nuclei. Collective model, vibration. In this particular slide, we are going to study the vibrational kind of collective model, because we have understood up to now that collective model can be of two types, the collective rotational model and collective vibrational model. So here in this slide, the focus is on the vibrational kind of collective model. A nearly closed shell nucleus has a spherical surface which is deformable, excited states oscillate about this spherical surface. So it means in this case basically we have the knowledge that nucleus in general is spherical in nature, but it is deformable. The excited states oscillates about this spherical surface. It means when the nucleus gains energy and angular momentum, in that case we say that the nucleus has excited. So that at the time of excitation we say that its nature changes from spherical to deformed. So it means that the nucleus in general is deformable, but the deformed feature we observe when the nucleus has gone into the excited state. So the deformed excited states oscillates about this spherical surface. Both spherical as well as deformed nuclei are capable of vibrating. So it means no matter whatever is the ground shape or size of the nucleus, every kind of nucleus is capable of vibrating. Whether it is spherical nucleus or deformed nucleus, both kind of nuclei has the ability to get the vibrational pattern. The collective excitations of nuclei due to vibration of spherical nucleus is different than the vibration of deformed nucleus. So, as we have said that vibration can occur in the spherical nucleus as well as in the deformed nucleus, but the kind of vibrations in the two nuclei will be different. In vibration, the nuclear surface assumes simple harmonic motion about equilibrium due to Coulombic repulsion, which we can interpret as negligible in nuclei with A less than 150. Collective model vibration. So we are continuing with our discussion about the vibration of nuclei. In case of vibration, the average shape is spherical, but instantaneous shape is not. So this is how we visualize vibration in nuclei, that the average shape of the nucleus is always, means while the nucleus is observing vibrations, its average shape is always spherical. But if we talk about the shape of the nucleus at a particular instant of time, then it is not. The moving nuclear surface can be represented by the following expression: r theta phi t is equal to r naught bracket 1 plus sigma lambda is equal to infinity, then again sigma mu is equal to minus lambda to plus lambda alpha lambda mu star t y lambda mu theta phi bracket close, where r theta phi t is the nuclear radius in direction theta phi at time t, and r0 radius of a spherical nucleus, while alpha lambda mu t are the multiple parameters. So what does this all means is that the nuclear surface is not just the spherical surface, it's not just the radius of the nucleus is not just r0, but a small other component also, which includes the vibration part. Collective motion, vibration. In this slide also, we will continue our discussion about the vibration in nuclei. Now, in the previous slide, we have understood the radius of a vibrating nucleus at a particular instant of time it depends upon various lambda and mu parameter, where lambda is the multipolarity and mu is the projection of lambda on the symmetry axis. Now, we would like to see the situation when we have different values of lambda. So, in the present slide, we will see the shape of the nucleus when lambda is equal to 0. Lambda is equal to if we put lambda is equal to 0, then this mode of vibration is called the monopole mode of vibration. And in the expression for radius, if we put lambda is equal to 0, we end up getting RT is equal to R0 plus alpha 00 Y00, where Y00 is equal to 1 by 4 pi. So it means the formula of radius becomes very simple. The spherical harmonics Yg0 is constant, so that alpha 00 corresponds to a change in radius of the sphere. Now it's very interesting to note that y00 is equal to 1 by 4 pi, which is a constant. So alpha 00 corresponds to a change in radius of the sphere. As large amount of energy is needed to compress the nuclear matter, this mode is far too high in energy. So this monopole mode is very high in energy, so its experimental signatures are very rare. The lowest excitation is in nuclei with A greater than 40 at an energy above the ground state, that is E naught is equivalent to 80 e to the power minus 1 by 3 MeVC. Collective model vibration. Now in this slide we are going to study how the nucleus behaves when we have lambda is equal to 1. Lambda is equal to 1 mode is called the dipole mode of vibration. In this dipole mode of vibration, if we put lambda is equal to 1 in the expression for r theta t phi, we get RT is equal to R average, that is R0, plus mu is equal to minus 1 to plus 1, alpha 1 mu, y 1 mu, theta theta phi, which reduced down to is equal to R average plus alpha 1 0, 1 by 2, 3 by 2 pi to the power 3 by 2 cos theta. So again in this case we find that the nuclear surface is a little bit elongated. The translation of nuclear fluid, that is oscillations of the protons and neutrons against each other and out of phase, gives this kind of mode of vibration. So it's just the translation of nuclear fluid. Translation of nuclear fluid means the proton and neutron oscillate against each other out of phase. Now this mode is observed at very high energies, that is around 10 to 25 MeV with respect to the ground state, depending upon the nucleus. So in even nuclei, this mode occurs at even around 77 e to the power minus 1 by 3 MeV above the ground state. Slide number 10, collective model vibration. We are continuing with our discussion about the vibrations of nuclei. In this slide, we are going to study the kind of vibrations corresponding to lambda is equal to 2. Now these kind of vibrations are called quadrupole vibrations. In this case, if we put lambda is equal to 2 in the expression for R, we get RT is equal to R average plus sigma mu is equal to minus 1 to 1, alpha 1 mu, y 1 mu, theta theta phi. And if we expand the terms with respect to different values of lambda, then what we get? We get V R average plus alpha 2 0 1 by 4 pi to the power 1 by 2, 3 cos square theta minus 1. So this is an expression for quadrupole mode of vibrations in nuclei. Now this mode is very popular and very common at low excitation energies in the nuclei. Collective model vibration. In this slide, we would like to see how the energy spectrum of quadrupole vibrations in nuclei looks like. So as we know that nucleus observe quadrupole vibrations which are quantized in nature. So amount of quantization is called the quadrupole phonon, that is the energy quanta in case of vibrations is called quadrupole phonon with J pi is equal to 2 plus. Now here on the bottom of this page of this slide, energy values are given for different number of phonons, and then the situation is represented like for n is equal to 0, n is equal to 1 and n is equal to 2. For n is equal to 0, energy value will be 0 h bar nu, 0 h bar omega. So we have the ground state as 0 plus. For n is equal to 1, we have 1 h bar omega, and this is 2 plus with an energy of 0.558. single phonon state. For n is equal to 2, we have the energy as 2h bar omega. There will be triplet of states like 0 plus, 2 plus and 4 plus at different energies. So, 2 phonon triplet do exist in vibration studies of the nucleus. Collective model vibration. In this particular slide, we continue our discussion about the collective vibrational model. Lambda is equal to 3 mode of vibration is called octopole vibrations. The octopole deformation is the principal asymmetric mode is the principal asymmetric mode of the nucleus associated with negative parity band. So, in this particular mode of vibrations are basically associated with negative parity band. So, when we have the energy level diagram for a given nucleus, nuclear energy level diagram for a given nucleus, then the characteristic which indicate that whether it has the octopole collectivity or not can be inferred if there is energy band which has got negative parity. So, this is the first signature that the nucleus can have the octopole collectivity. Octopole modes with lambda is equal to 3, W by J pi is equal to 3 can be observed in many nuclei. It means the octopole mode of vibration or octopole collectivity, which we can say, is observed in very many nuclei across the chart of the nuclei. Collective model vibration. Now, in this slide, we would like to see how the shape of the nucleus changes with changing value of lambda, that is in moving from lambda is equal to 0, that is sphere, to super heavy elements like uranium, thorium, etc. So, here in the picture, different shapes of nuclei are given corresponding to lambda is equal to 0, that is spherical shape, lambda is equal to 2, that is quadrupole shape, then lambda is equal to 3, that is optical shape, and then at the last hexadecapole is there for lambda is equal to 4. So, we can see that for lambda is equal to 2, the nucleus can be oblate and prolate, while at lambda is equal to 3, the nucleus assumes the octopole shape, and for lambda is equal to 4, the nucleus assumes hexadecapole shape. Collective model rotation. So, up to the previous slide, we have discussed the collective mode of motion which produces the effect of vibration. Now, in this slide, we are going to study the collective behavior of collective motion of nucleons in deformed nuclei, which gives an impression of rotation of the nuclei. In shell model, core is at rest and only valence nucleons move. So, as per the shell model, the properties observed in nuclei depends upon the properties of or the motion of valence nucleons only. If nucleus is deformed, core plus valence nucleon rotate collectively. So, it is very important for nucleus to be deformed in order to observe the quadrupole rotations. So, when the nucleus is deformed, core plus valence nucleons rotate collectively. We would like to see how much is the energy of a rotating nucleus. So, in case of rigid rotator means in which there is no any other scope of any change, means the distance between two successive particles in the object is fixed. So, that defines the rigid rotator. So, energy of rotation of a rigid rotor is H rotational is equal to R square over 2I. Now, we need to basically find the solution of Schrodinger wave equation, that is H psi is equal to E psi. It implies that R square by 2I psi is equal to EJI, where R square YLM is equal to J into J plus 1 H bar square YLM. So, with this kind of formalism, we can basically discuss the energy of rotating nucleus. Collective model rotation. So in this slide we are going to see, or we are going to look at how the expression for energy is different here than in case of vibration. So here we notice that the energy corresponding to energy of a nucleus with spin j is given by Ej is equal to h bar square by 2I j into j plus 1. So j is equal to 1, 2, 3, 4. As there is reflection asymmetry, so odd j is not acceptable. So allowed values of j has to be 0, 2, 4, etc. As there is reflection symmetry, so odd j is not acceptable. So allowed values are j is equal to 0, 2, 4, etc. With these kind of conditions, we have the formula of rotational energy part of rotating nucleus as Ej is equal to h bar square upon 2I j into j plus 1, where j is equal to 0, 2, 4, etc. E0 is basically the ground state, E2 is the 64 state, 64. E2 is basically much higher in energy and is given by h bar by 2I, 2 into 2 plus 1, that is 6 h square by 2I. First excited state energy is equal to h square by 2I, that is equal to 1 by 6 h bar square, 1 by 6 E2, and then Ej is equal to 1 by 6 j into j plus 1 E2. Collective model rotation. Now in this slide we will see, or we will basically compare what kind of energy spectrum we have when a deformed nucleus is undergoing vibrations and the deformed nucleus is going rotation. In the left hand side picture, the vibrations of an axially deformed nucleus 134 rpm are shown, whereas on the right hand side picture the rotational energy levels of an axially deformed nucleus 238 uranium are shown. In the left hand side picture we observe a ground state band, a normal ground state band, and two additional side bands as gamma band and beta band. What is the meaning of gamma band and beta band? Gamma band, beta band arise when the nucleus is deformed. If the nucleus is axially deformed, that is, we have beta value, we have some beta value for the nucleus, but gamma is equal to 0. In that case, if such a nucleus vibrate, we have some additional energy levels which we group as beta band. On the other hand, when some triaxiality is there in the deformed nucleus, then the vibrations of the nucleus basically give a number of energy levels which form a band and which we label as gamma band. So gamma band and beta band are nothing but the vibrational energy levels band with respect to two different kinds of deformation. On the right hand side picture, we see that the energy sequence is a normal what we should expect for a rotational energy sequence. Like the energy levels are separated in the ratio of, or in terms of I into I plus 1 rule. So 0 plus, 2 plus, 4 plus, 6 plus, 8 plus. Here we can see that the energy separation between two successive levels is increasing in the order I into I plus 1. So it's a typical rotational energy sequence for an axially deformed nucleus. So students, let us summarize what we have learned in this module. The first thing that we have learned in this module is that collective excitation is due to the coherent motion of valence nucleon. Second thing, what we have learned is the spherical nuclei can only undergo vibrational collective motion. Third important thing that we have learned is that deformed nuclei can undergo both vibrational and rotational motion. Next important thing that we have learned is that for deformed nuclei, only quadrupole mode of motion is significant. And the last thing that we have learned is collective model improves the understanding of nuclei further.